So what we're doing today is going to review Module 5 quickly and briefly before moving on to doing lots of practice questions. So the first section of Module 5 is projectile motion. We understand projectile motion is talking about the motion of a projectile, which importantly moves only under the influence of gravity. This projectile is launched at some velocity v at some angle theta, and then it will undergo projectile motion, which is a parabolic arc. Importantly, because it moves only under gravity, then we are ignoring air resistance. Now, through Galileo's experiments, he tells us that the horizontal and vertical components are independent. And because they're independent, we can treat them separately. By doing a free body diagram analysis, we can see that the horizontal component has no force. So therefore the acceleration is 0. The vertical component, the force of course is weight. And therefore the acceleration is negative g. So the key thing you need to understand, of course, is that there is no acceleration in the horizontal direction, but there is a constant acceleration in the vertical direction. That, of course, results in velocity being constant. And having a constant downward acceleration means you've got a linear velocity. We then use your decomposition of vectors at the start to work out our ux and uy. So we understand, which should not be difficult, to understand that ux equals v cos theta and uy equals v sin theta. Just considering that you're launching at theta with v. So keeping this in mind, we now are going to get our equations. So basically, because acceleration is 0 and acceleration is negative g, that means acceleration is constant in both directions. So we can use our Suvat equations, which include v equals u plus at and s equals ut plus half at squared. In the horizontal direction, we understand, of course, that a equals 0. U x, if you like, equals v cos theta. That instantly gives us our velocity in the x direction is v cos theta plus 0 times t, so it's just v cos theta. And your sx equals, well, the a is 0, so that goes completely, so it's just v cos theta times t. Or in other words, ux times t. In your vertical direction, your a is negative g, which is still constant. Your uy equals v sin theta. And so your vy equals u, which is v sin theta, plus a, which is negative g, times t. And there's your vy. Think of that as vy minus gt. And your sy is going to be, well, your v sin theta times t minus a half gt squared, otherwise known as uyt minus a half gt squared. So those are your formulas. The key thing to note with these formulas are these are all time equations. So when you're using these formulas, the key thing is to basically solve for time. And that's basically the formulas we'll be using in physics to answer projectile motion questions. Now, briefly, we understand that horizontally, Let's draw our ST, BT, and AT graphs. In the horizontal direction, we said there is no acceleration, a equals 0. That means it's going to have a constant velocity, which will look like that. And that means displacement will just simply be going up in a linear fashion. Acceleration here will actually be negative. So it should be here. Velocity will be linearly decreasing like so. And the displacement will be like a parabola. So in fact, this means that there is no a equals 0, as we expected. This is constant, and this is linear. Looking at the horizontal, of course. Whereas the acceleration, this is constant. This is linear. This is parabolic. Okay. This, of course, is at negative g. If you solve, you can get this point in time, which would be in the v sine theta over g. And this, of course, is 0. This, of course, is ux, which is v cos theta, which means this gradient is v cos theta. So often you are tested in multiple choice, particularly on sort of this aspect, constant horizontal velocity, and this aspect, constant vertical acceleration downward, and very similarly constant horizontal velocity that there is no acceleration. The others are good to know as well, but the most commonly tested ones are the ones that have been asterisks. Some other key, just brief concepts that we'll quickly cover is that we have the concept of some terms. You've got range, which is how far it goes across horizontally. You have max height, which is, as the name might suggest, the maximum height the projectile reaches. And you have time of flight. Now, you will need to know how to work all of these out. Don't bother remembering the formula, especially for physics. You will have to demonstrate using the 6 equations we showed before how to do that. I'll only run through the how in a moment. But before I do that, I'll just quickly mention some key facts as well you might wish to be aware of. If projectiles have the same max height, doesn't matter at what angle they're launched and what velocity they're launched at, if they end up with the same maximum height, and if they start on the same position, ground and finish at the same ground, and they all reach the same max height, even if they're launched at a different angle and different velocity, like that, then they will have the same time of flight. The time of flight and the max height are linked in the sense that if you have the same time of flight, you have the same max height. If there's the same max height, you have the same time of flight. Range is maximum at theta equals 45 degrees. Anything less than 45 degrees, for level ground, to be clear. If you are at anything not at 45 degrees, then for any other point, so here, which is clearly less than maximum range, since I've been able to get here, for example, then there are always 2 angles that you can hit. You can do it like that, or you can do it like that. Okay. In other words, for any range that is less than max range, there are 2 angles that can hit that spot. If one of them is alpha, then the other is 90 minus alpha. The projection angles are complementary. So you can think of it as alpha and 90 minus alpha, or you can think of it as 45 plus an angle and 45 minus an angle. So for example, 40 degrees, you can think of as, well, 90 minus 40 is 50. So 40 and 50 will give you the same range. Alternatively, 45 minus 5 is 40, 45 plus 5 is 50. Either way. And the other thing that might be helpful to know is if you are launching a projectile on a level ground situation like this, with velocity v and angle theta, then when it lands, the landing velocity of a projectile on level ground is also going to be v and at angle theta, below the horizontal in this case, but it will still be theta. Now we can of course prove that mathematically if we like, and you should know how to do that. So basically, if you were to prove it mathematically, one way to do it would be to find the velocity in midair, except on the ground. And just quickly recapping, to find the velocity at any point in midair, you need to find the velocity in the x direction at that point, the velocity in the y direction at that point using your time equations, and then basically add your vectors together. And if you do that for here, you will show that. But another way we could sort of prove it without doing those equations is think about it in terms of conservation of mechanical energy. You've launched the projectile, it's got some mechanical energy. Some of it's going to convert into GPE, but then it's going to be converted back into KE. So at this point, we've got the same amount of KE as before, so it should land at the same velocity. Okay, so those are some key ideas you should be aware of. It can save you a lot of time in multiple choice questions. Now let's talk about how to derive the sort of range, max height, time of flight. I won't focus on the formulas, I'll just tell you the how. And you should all definitely know how to do this. If you don't, this is very important. This is tested basically, some of it, if not all of it, will be tested basically every single time. So remember what range is, remember what time of flight is, and remember what max height is. So time of flight is simple. You know it's going to land here. So what we know is that the vertical displacement is, for level ground, the same as this. If it's not level ground, the vertical displacement is still known. You still need to know how far off you are at the cliff and so forth. So basically, let your vertical displacement equal 0 or applicable, if not level ground, and solve for t. If it's confusing, ignore you'll get two answers because it's a quadratic. Ignore t equals 0 or negative t values if you're not on level ground. Go for the positive t value that's not 0. So that's how you get time of flight. Some students like working out time of the max height and then doubling it, which will work for level ground, but I think that's probably not as good an option because you can't rely on that when it's not level ground. So it's better to go for a way that will work for all options. Okay. So once you have the time of flight, you can get the range very easily. The range is, well, the x. So basically, once you find the time of flight, see left. If you don't have the time of flight, find the time of flight using this. Then sub the time equals the time of flight, whatever number you worked it out to be, into Sx equals Ux times t. So in other words, the range will be your Ux times your time of flight that you've worked out. And in physics, things are usually numerical, so I'm going to just leave them like that. And then you've got your max height. So your maximum height is going to be, find the time we basically need to know something about the maximum height. And if you think about it, your particle's kind of going up, stopping, and then coming down. So basically, you let the velocity in the y direction equal 0 and solve for t. And we'll call this time at the max height. Max height is a vertical displacement, so we sub t equals time of the max height into sy. And then you'll get a value for max height. The steps for each of these are imperative to know and should hopefully not give you any major problems. For those of you doing 3-net or 4-net maths, then of course you'll know that you're also doing these in projectile motion, but treating it much more algebraically. Okay, so that's basically projectile motion done. We'll be looking at questions in a moment. Let's move on to circular motion now. So we're going to quickly review circular motion theory here. Of course, what does circular motion mean? Well, circular motion is talking about when a particle undergoes circular motion, as in my diagram on the left. Now, when a particle undergoes circular motion, it will experience velocity that is in the direction of the tangent. In other words, the velocity is always tangential. And because velocity is a vector, that means it's changing direction. It's got both magnitude and direction. And you can clearly see that as it goes around the circle, it's changing direction, which means there must be acceleration. And that acceleration can be proven, but we won't do so, to be towards the center. And hence is given the term centrifugal acceleration. So for circular motion, velocity is tangential. Regardless of whether you're speeding up or slowing down, even if you're going at the same speed, there is acceleration involved to maintain a circular motion. And that is towards the center and has a magnitude of v squared over r, or r omega squared, where v is linear velocity and omega is angular velocity. So remember, while you are often given v, sometimes omega may be required, or sometimes covariance is useful. So there is also this relationship, v equals r omega, where of course v is linear velocity in meters per second, and omega is angular velocity in radian per second. Okay, so the C is for centripetal, which basically refers to the fact that it's towards the center. Now, this is going to be a very key fact, or the next one. So when you have acceleration, you know from Newton's first law that acceleration does not occur without a net force. And in fact, from Newton's second law, F equals ma, you know that to get an acceleration of AC, you need a force. And this force is the net force. And this Fc would just be mv squared over r, or m r omega squared. So the key point to recognize here is regardless of the type of circular motion you're undergoing, whether it's uniform or not, in other words, whether you're going at the same speed throughout the circle or not, all the ones you're doing are likely to be uniform. They're basically not going to ask you any questions on non-uniform circular motion in physics. But even if it wasn't uniform, and it doesn't matter whether this circle is horizontal, vertical, on an inclined plane, anything, any type of circular motion, merry-go-round, planets, you're always going to need a centrifugal acceleration, which is related to the velocity and the radius. And to achieve that acceleration, you're always going to need a net force. Now, remember, this isn't a net force, this is the required force. So it's not an actual force that exists in and of itself. It is not a force like gravity. It is not a force like
magnetic force. It's not a force like normal tension, but it is the force that is required. It's like a cost.
So this is the cost of undergoing circular motion.
If you have forces that can supply the force to pay the cost, then yes, you can make the particle undergo circular motion. If you can't make something undergo that, then it won't. Okay. If you're bigger, and it has to be this amount. If it's bigger or smaller, then it's not circular motion. You'll end up with a spiral. Okay.
Now,
if you understand this is the tangent and this is towards the center,
then it might also be helpful to note at this point that
these are at right angles to each other, always. And this then is also why, since we've done module 6 already and 8, just note as well, while we're on this topic, that if you've got a charged particle in a magnetic field, it will undergo circular motion. Okay, it will undergo circular motion because the magnetic force is going to be perpendicular to the velocity.
And the radius you can determine is equal to mv over qv. We will review that when we get to that part,
but basically that relates very much to this section we're talking about. And while we're at it, we might quickly also mention here, if you have, we'll do it on a new page.
So basically, quickly reviewing what we've just done, if you've got a charged particle entering an electric field, then it will undergo projectile motion. And that's because the force of the electric field is equal to QE, which is constant. It's constant in magnitude and direction. If you enter a magnetic field, then it will undergo circular motion because FB equals QVB sine theta. Usually theta equals 90 for our questions. So it's constant magnitude, but for an electric field, it's constant direction. You can see that in just a very simple diagram. If this is positive and it's heading to the right, your electric field is heading downward. And so your projectile will curve,
but as a projectile motion.
However, in the case of the magnetic field, although it's constant magnitude, the direction is continually changing. And more specifically, it is perpendicular to your velocity. So if you've got a magnetic field that is going into the page, for example, and you've got a charged particle entering like so, then using your right hand, okay, I'll make that negative, or I'll just change where it enters actually. So if you use your right hand push rule, you'll note that with this magnetic field and velocity direction, you'll get a force upward, which will cause it to change direction, which will change the direction of the force. And so basically the trajectory of this particle will end up going in a circular fashion.
And it will actually only go through a semicircle. The fact it's still a circular arc, it'll only go through a semicircle before, well, coming back out, because the only way you can get it going through a full circle is if it starts in the middle of the magnetic field. So particle goes in and then you turn the magnetic field on, and it'll undergo circular motion, like a whole circle. Anyway, regardless, the point is, the key points are electric field, projectile motion, magnetic field, circular motion. Okay. And really, that's all the theory there is to circular motion. You can apply them very broadly, along with your skills in your free body diagrams and so forth, from year 11, your force analysis, to basically apply them to any circular motion question.
Okay, and then of course we've got gravity and sort of applications. So the key thing you want to understand here is that you've got, for example, the gravitational force from Newton's universal law of gravitation is g m1 m2 over d squared. Note, of course, that d is the distance between the centers. So that's one of the key formulas you'll need going forward. So recognize that g is the gravitational constant, okay, universal gravitational constant, which is 6.67 times 10 to the negative 11. That, of course, is on your formula sheet. M1 and M2 are just masses in kilogram of the object, and Fg is, of course, the gravitational force. The gravitational force is, of course, a non-contact force. Being a non-contact force, it has a gravitational field and associated energy levels. Now, the key difference now, looking at this, is you recognize the gravitational force follows the inverse square law. It's proportional to 1 over d squared. So unlike what we assumed back in year 11, where the weight force, which is a gravitational force, is just mg, we can actually see that it depends on how far away you are from Earth. We've assumed it was g because we were always talking, a few hundred meters at most within Earth. So it didn't change much. If you check the calculation, it won't change much. And d is from the center of the planet. The planet is radius of Earth is 6,400 meters, kilometers. So changing an extra 100 meters or so wouldn't have changed much. Right? This is the radius of Earth, which is about 6,400 kilometers. And if you're, changing 100, you're changing an x less than 1 kilometer out usually, and so difference is negligible, and you're always around g. On that token, we can use the fact that if we sub in d equals the radius of Earth, we can basically get the fact that the g of a planet is equal to g times mass of the planet over d squared. That's also something helpful to note. Okay, and if you sub in the values for Earth on that, you should get about 9.8. Now, given that, with gravity, we also recognize that, well, you also can calculate GPE, but GPE is now affected because in the past, GPE was just calculated as mgh, but we now define GPE to be negative g m1 m2 over r, and you can calculate this using integration if you're so inclined. It's basically the integral of the force from, but the key points to know with gravitational potential energy are GPE is always negative for all points. And the reason that GPE is always negative is we're trying to show the fact that potential energy is meant to show you about potential energy, how much energy you have to do things. Now, if you've got a positive GPE, you should be able to kind of have excess energy to do things like move and things like that. But the thing with the gravitational field is that it extends to infinity. So even if you're out at a very, very, very far distance away, if you have stopped, you are still being pulled back to Earth, assuming there are other planets pulling you out towards them instead. So assuming there's only one object in the universe, being Earth in this case, even if you're a very, very far distance away, you're still going to be gradually pulled back. And it might take 1,000,000 years or more, but ultimately you're coming back, which means you didn't escape the gravitational field and you still have a negative amount of energy. And that's why 0 is defined to be at an infinite distance away. Of course, you can never actually be at an infinite distance away, but that's the idea, okay? The idea is to be at an infinite distance away, and that's when your GPE equals 0. So we know GPE equals negative g m1 m2 over r. Now we're going to then talk about the concept of escape velocity. So escape velocity is when you've got an object and you propel it with some initial velocity. And you just imagine it's like a projectile. And our aim is to just get it to continually leave. For you to do that, you must propel it with sufficient velocity for it never to come back, which means we're giving it kinetic energy, which we know is half mv squared. As we discussed, we want to be able to get the object not to come back. That means you need the total energy to be positive. And that's basically how you derive escape velocity. So you let GPE plus KE to be positive, and if you derive that, you'll get the escape velocity must be greater than square root of 2gm over r. Kind of like projectile motion, knowing the final answer is not as important as knowing how to get it. We'll also briefly couple Kepler's 3 laws. So Kepler's 3 laws are: 1, the law of ellipses, which basically says all orbits are ellipses, with the mass being orbited out of focus of the ellipse. 2 is the law of equal areas. And the law of equal areas basically says that the amount of the area covered by a ray between the orbiting object and mass orbited is the same. For each unit of time. The keynote you probably want to take away from that is the corollary, the result of that is in an ellipse, there are bits that are, I've drawn a very extreme ellipse, but let's say your sun or whatever is being object is over here. Okay. And you've got, let's say, Earth or whatever going around. So the key point here is as you're far away, this section is slow. When you get close, this will move really quickly. So your velocity when you're going in your orbit in an ellipse is not actually constant. So the orbit speeds up as you approach the orbiting mass. Now, in a moment, we'll be doing calculations with orbits. Just know that although we know that all orbits are ellipses and that the velocity is not constant, for our course, we assume, for simplicity, that the orbits are circular and the velocity is constant. Okay. So first 2 laws, you don't really need to worry about in terms of calculations. They may come up in a multiple choice question here or there as a brief marker, but the one that's sort of really more important in terms of how often it comes up in exams is the 3rd law. That's called the law of periods. And basically, that's just numerically r cubed over t squared. R1 cubed over t1 squared is r2 cubed over t2 squared. So basically, you take anything that's orbiting the same object, so planets around the sun, for example, or moons around a planet, like multiple moons of Jupiter around Jupiter, and the ratio will be equal. If you're using it like this, then as long as you're using the same units for r and t, then you're fine. Whether that's SI units like meters and seconds, or you could be kilometers and hours, or you could do light years and days, or you could do astronomical units and years. It doesn't matter. If you're using this form, as long as the units for R1 and R2 are the same, and T1 and T2 are the same, then you're fine. As long as your units are consistent. Now, we can actually also prove that r cubed over t squared equals gm over 4 pi squared, and that's what's on your formula sheet. If you want to use this version, because you're using g and m and so forth, then you must use SI units. In other words, r is in meters and t is in seconds. And you will use that to do that. Now, you may also be asked to prove r cubed over t squared equals gm over 4 pi squared. I won't run through the entire proof with you. I'll just talk to you about the how. So firstly, you'll need to recognize that for something to undergo circular, and this is, I guess, a pretty key point, you understand that if something is undergoing an orbit, then it's basically undergoing circular motion. Okay. So if something is undergoing a stable orbit, then it's undergoing circular motion. In our course. And we assume uniform. It's not speeding up or slowing down. But as we discussed earlier, to have circular motion, that means you need centrifugal force. This is the required force. But the required force, centrifugal force, which is towards the center, is in reality being supplied by gravity, Fg. Now we assume in our orbits, and hopefully so, that there is no other force acting on it except gravity. So when you do consider what forces act on an object in space, the answer is none, okay? Apart from gravity. So this is the supplied force. And because that is the only force, then it is also the net force. And so we basically let these two equal, okay? Now, if you just directly let these two equal and solve for V, then you will get a formula we need, which is orbital velocity. I'll write that out on the next page, just because, just for constraints of time, of space. But here, if you let F equals Fg, you don't really get this 4 pi and r involved, okay? Then you'll end up with a V, right? You have a V that you don't have here. So what you need to then consider is how to get rid of V. Now V is the velocity, okay? So you're going around at some velocity V. And if you think about it, in t, in a period, in time t, you have completed one revolution. Which means that the planet completes one perimeter in t seconds. So therefore, velocity is displacement over time, but displacement is 2 pi r being perimeter of the circle divided by period. So basically, to prove this formula, you just simply need to, 1, let the centrifugal force equal the gravitational force using the formulas we outlined before, and sub in V equals 2 pi r over t. Do a bit of algebra, and you'll get that. We've done it before. I'm just quickly reviewing the steps. Okay. And you then that's proven. Okay. So as discussed, very importantly for orbital velocity, we assume circular orbits. We assume, therefore, uniform speed. That lets us say that, and of course, the only force is gravity. That lets us go with Fc equals Fg, which you might recall is mv squared over r equals g m1 m2 over r squared. And solving for that, you'll get velocity orbital equals square root gm over r. So I'm focusing here on the how to do it, but I'm leaving for you to do the work yourself. And then so we have more time to go through actual questions. Now, we also might recall that the escape velocity from earlier, which was done as a reminder as ke plus gpe is positive, gave you 2 gm over r. And so you might note that the escape velocity is root 2 times the orbital velocity. Which of course means that the escape velocity is larger than the orbital velocity. And that makes sense because, of course, if you think about it, if you're in orbit around a planet, right? If here's your planet, and you're going in an orbit around it, then you haven't escaped the gravitational field, right? You're not falling onto the planet, you're going around it, true, but you haven't escaped. You're stuck in the gravitational field. That's why you're still around the planet. If you were free of the gravitational field, you'd be going off and doing your own thing, regardless of the planet. So it's clear that, well, even though you've achieved orbital velocity and no longer fall back to the planet, you haven't escaped. And it does therefore make sense that the escape velocity is higher than orbital velocity. It might be worthwhile to note that both orbital and escape velocity depend on the mass of the planet and how far away like the orbit is, or if you're escaping from the planet of Earth, then the radius of the planet. Okay. So the bigger the planet physically, the lower the escape velocity and orbital velocity. The more massive the planet, regardless of size, then the higher the orbital and escape velocity. So theoretically, you could have a very big planet that's not very dense, then you could have an orbital and escape velocity that are very low. Okay. You might want to also recall that if you're in orbit, then you are moving. If you're in stable orbit, you are moving with a velocity equals orbital velocity equals root 2g root gm over r. Now, that also means if you take a look at orbital velocity, that for any particular altitude, you are at a particular r, right? This is r. Once you know r, and you know what planet you're going around, which sets m, your orbital velocity is set. So you don't really have a choice in your orbital velocity. If you determine you want your orbit to be at a particular altitude, then you have no choice with regards to orbital velocity. And it might also be clear from the formula, as r goes up, then your orbital velocity goes down. So orbital velocity actually increases as velocity goes down, or as r goes down. The closer you are to the planet, the faster you need to orbit in that sense. The further away you are, the slower you need to orbit. Now, you've learned before that mechanical energy equals kinetic energy plus potential energy. We know that if you've got a satellite going in orbit, it's got to be traveling at this velocity. So the kinetic energy, of course, is going to be half m times v orbital squared, which is going to be half times the mass of the satellite, to be clear, times g mass of the planet over r. Now, this satellite also has a gravitational potential energy. which we've already said earlier is negative. It's g mm over r, so it's mass of the satellite times mass of the planet over r.
So the total energy, the total mechanical energy, is just the sum of these two. Hopefully you can see that these are the same thing. It's just that this is half of it. So think of it like half x minus x, right? You can factor that out if you like. But basically that means the result is negative half g mass of the satellite mass of the planet over r. And that therefore is the energy total of a satellite in orbit. That's the calculation side of things. But in terms of just overall concepts, as you go further out, your GPE goes up. And assuming you have the same amount of mechanical energy, because then that means your KE goes down. And while we are now using different formulas to when we were doing in year 11, in terms of GPE, due to the varying gravitational field, the concept still applies, right? In the sense that you still have the mechanical energy, and we still have the fact that you need to do work to get away from the planet. So although it's not MGH anymore, we still have, with looking at the formula or not, you still need to do work to get away. So as you go away, GPE goes up. And as a result, the KE will go down. And you can also see that in terms of orbital velocity as well. Conversely, of course, as you go in, then GPE goes down and KE increases. Now, to be clear, of course, even though I've drawn the arrows like this is just representative. Of course, if you're in orbit, it won't just go straight out or come back down. Reality is that it will be slowing down to sort of spiral in, right? If it's dropping in, or alternatively, if you're going out, then if you speed up, it will start spiraling out. Over, I'm exaggerating here, but obviously it will be over many, many revolutions. And that's when you do your Hoffman transfers and things like that. Okay, so that should basically cover all the module 5 theory and so forth. So now basically let's get a start on questions.